On page 42, we're talking about a definition of the area of surface of revolution. So what I'm going to do is take the diagram that I drew on the previous page and actually spin that around I'm going to spin that around the x-axis. All right, over the interval of a to b, all that good stuff. All right, so there's some stuff that I want to get rid of, All right, so the first thing we do is we actually spin that little arc length around, because all I care about is the surface. I don't care about the volume. So what I would do is take this little segment here, this little guy, and spin it around. Let's put it here, here, and draw a little line segment. Alright, so this is getting spun around. I'm just showing the half circle, the part that's going into the page. And then we do the same thing for every other line segment along the way. Right, every other infinitesimal line segment is really what we're looking to spin. Alright, so you'd end up with a surface. Or at least that's the goal. So the question would be, well, how would we do that? Well, something's going to act like a radius of a circle, right? So previously when we talked about the volume, we talked about area with thickness. Well, if we talk about circumference, so surface area of an infinitesimal arc would be the length multiplied by the circumference. And so previously we had for volume specifically, we had an area, a bounded area, multiplied by some kind of thickness. And that bounded area gave us the radius of a circle, and we used pi r squared to come up with the area of a circular slice. Here what we're going to do is use 2 pi r to come up with the circumference of a circular slice, with arc length serving as the thickness. All right, and embedded within that thickness is a d something, dx or dy. All right, so we have the 2 pi r, and we have an arc length formula, which is 1 plus f prime of x, for example, dx under the radical, over the interval a to b, all right, the other possibility, I don't know where, copy's in the front now. All right, they updated. Or it could be going from C to D. I like to switch up the bounds just to distinguish. but everything would be in terms of y. All right. And so as long as you come up with some expression that represents the radius, because we know it's not constant in this case, the radius is whatever this function is. Y would be f of x. All right. So in that case, we would represent our formula where radius is some function of x. All right. As opposed to the vertically oriented case where you can kind of imagine it would be reversed perpendicular, where r would be a function of y. So if I want to find the surface area formed by revolving the graph of x cubed on the interval of 0 to 1, first I'll do a quick sketch. 0 to 1, well, the graph normally looks like this, but I only care about the 0 to 1 part of it. So it's really just this piece. About the x-axis, what I would do is take a little segment here and spin that. All right, so I'd be looking at 2 pi over the interval of 0 to 1, the radius function, the radius between the axis of revolution and the point on the curve, r of x, well, we have y equals x cubed. That's my r of x function. So x cubed multiplied by, well, I would need an f prime of x, 3x squared. So I'm looking at 1 plus 3x squared dx. So 2 pi, math 9, 0 to 1, what? 0 to 1, x cubed, square root of 1 plus, I'll type it in as 9x to the 4th, dx. And so we're looking at about 3.563. Now it's a measure of area, so units squared. All right. So for the next one, y equals x squared. Spun around the y-axis over the interval of 0 to rad 2. So we're talking about just some segment that's getting spun around the axis. I'm going to need r of y here. All right, some function of y. Since y is equal to x squared, x would be equal to root y. And so that's going to be my r of y. Since this function will be defined in terms of y, I have my f of x here as x squared, but we need f of y. So y is equal to x squared, as we know. X is equal to the square root of y, making f of y equal to the square root of y. So, all stuff we talked about already, but I wanted to make it all official, like y to the 1/2 is what the square root of y is, making f prime of y equal to 1/2 y to the negative 1/2. So we have all the ingredients. Now it's just a matter of integrating. So 2 pi over the interval of 0 to, well, actually, one sec, these are x bounds. All right, so I would need the corresponding y bound. So let me find f of 0, which is 0 squared, which is 0. F of rad 2, which is rad 2 squared, which is just a 2. So going from 0 to 2, r of y, so the square root of y, multiplied by the square root of 1 plus 1/2 y to the negative 1/2 quantity squared dy. All right, so that's what I'm going to run through the calculator. 2 pi, math 9, 0 to 2, rad y, multiplied by the square root of 1 plus, already that's 0.5, y raised to the negative 0.5 power close it up, square it, and we're out of the radical, it's closed, and dy. So about 13.614. And this would be square units. All right, so on Desmos, we could type it in, but what I did is I created, and this is all on Blackboard, this is a vertical axis. I created a surface area calculator. All right, it requires you to put, if you're using the vertical axis of revolution version of it, you'd have to put it in as a function of y. So I saved all the particulars for this particular problem. All right, so what's the function in terms of y that's going to be revolved? The square root of y, because that's what this is in terms of y. What are the bounds? We had to figure that out, going from 0 to 2. What's my axis of revolution? X equals 0 because it's a vertical axis. K is the horizontal movement. That's more for a visual. I'll show you that in a sec. And then it'll compute the surface area for you. And so it really is just a matter of the setup. All right, but I put this in here so you can actually see that infinitesimal little bit of arc length that's being revolved around the axis. All right, collectively, each one of these circumferences gives you, when you add them together, each one of these circumferences first gives you a slice of the surface area, and then collectively gives you the total surface area. All right, but I'm going to resize this and put it away, and there it is.